Okay, hello everyone. My name is Zhong Yiho. Thanks for joining this design automation webinar. So this is a third event for our DOM, and this is organized by CDA, which the organizer, whose organizer is Ilan Chen, and I'm the representative from CEDA. And this topic will be related to secure silicon and talking about the recent developments and up challenges. So for this event, we have four prominent speakers. They are Brandon Wang from Synopsys, and Mark Terani from University of Florida, and Gang Ku from University of Maryland, and Ahmad Reza Sadehi from TU Darmstadt. And this time we specially appoint the Professor Ye Jin as our moderator. I think everyone knows Ye. He's a hardware security expert. So I think it's good to have him to moderate this event. So I will quickly go through this slide. So first I will give a welcome remark, and then the first speaker will be Brandon Wang. He will talk about the key to hardware security. Yeah, and Mark will talk about the automatic implementation of secure silicon. Typically, is the overview for his recent development for the ICE program. And third speaker, Professor Gang Ku, will talk about the assessment of hardware security and trust. So first three speakers are related to the DARPA ICE program. And last but not least is the talk about enclave computing on RISC-V, a brighter future for platform security. So Ahmad, he will talk about his recent work on the hardware security on RISC-V, and also he will talk about the recent development from the perspective from Europe. So each talk, after each talk, will be followed by the 5-minute. Hi Ahmad, thanks for joining us. Yeah. So each talk will follow by the 5-minute Q&A. Then for each speaker, at the end of the event, we will have a 15 minutes for Q&A for all speakers. So now I want to do some advertisements. So now we have the two call for papers for journals. One is the IEEE JET case. Yeah, it's a special issue for hardware security. And another one will be the JETC. It's related to the trustworthy AI. So the last one will be I hope all participants will join the membership of HM CDA and the IEEE CEDA. Yeah, so we really need you, yeah, as a volunteer and also the experts in both communities. Okay, thank you. I think I want to leave more time for excellent talk today. So now I will hand over the host to Professor Ye Jin.
Okay, thanks for joining the. Zhongyi, can you keep the slides on? That looks very good. Oh, Brandon, can you just show your slides? So.
Sure.
Thanks. So it's a very high profile hardware security panel. So I will keep my introduction very short. Brandon is the vice president at Synopsys, and he is overseeing the strategic activities. So to be honest, I'm not quite understand what it means of strategic activities. Until recently, Brandon kind of like guide Synopsys going through the ACE program. That gave me an idea, a very vague idea what this strategic activities means. And I look forward to the talk to Brandon to learn more about the strategic activities.
All right, shall we start?
Yes, Brandon, you have 20 minutes plus 5 minutes.
Okay.
Q&A.
Okay, I'm gonna zip through pretty quickly. Thank you everybody for these opportunities. I will cover a little bit high level on hardware security, and we have expert Mark that we work together on the ACE together. Gan and the rest of the expert will probably go deeper on the technical side. Can you guys see my screen?
Yes.
Okay, super.
Yes.
So let me give a brief about Synopsys is about. Synopsys is from silicon to software. We cover 5 areas: software, security, quality. Verification covers leading semiconductor and system company to cut design schedule by helping them verify advanced silicon chip together with the software. The IP, we have a large portfolio to enable customer to reduce the risk and spend time to market with the industry, probably the broadest portfolio of high quality silicon proven IP. Design group is really the core EDA that our digital custom analog mixed signal design tool to help customer achieve the best result of productivity and optimize the power, performance, and area. The last one, silicon engineering group, is our pioneer TCAD and lithography solution that used to develop the next generation process and device modeling for manufacturing. So now, that's why we see there's a growing market for semiconductor in 3 areas. One is the AI, the second is automotive, and the third one is IoT. So what are common in these 3 areas? The common thing is that safety, security, and reliability are all needed, are much more needed in all these 3 growing segments. As you probably heard the story about the hackers, get into the casino through the fish tank a couple years ago. And things could get worse in a car. That's the Wired magazine reported about 3 years ago. It's really dangerous because the hackers can actually infiltrate it by, bypassing the whole the anti-hacking shield of automotive. And the other example is the Ford magazine reported that this person have never get onto the airplane but be able to control from the ground, okay, by connected to a passenger on board, okay. So these become a more serious things that the semiconductor industry really need to look at it. Not only the traditional security that covers network and software, but also go deeper to say, hey, we need to look at it, the chip level, the IP level, and all the sensors associated with the system. And that need the semiconductor engineer, semiconductor design engineer, design the hardware with the security in mind from the beginning. So as people in silicon knows that our software is really look at optimized PPA, power, performance, and area. Now, we have added 1 dimension to that matrix, and that is to add security on it. So we need to optimize our design on power, area, speed, and security. And that is what PAS is about. You probably heard the PAS term in the ACE program announcement. So PAS is a evolution of semiconductor design matrix from PPA, power, performance, area, to power, area, speed, and security. So let me give more detail on why we need to have this additional security on top of what we already done in the network and software security domain. Let's discuss some common hardware hacking terminology. The first one came up is reverse engineering. One common way to reverse engineer is to do deep packaging of parts and examine it. See the picture on the screen is a picture taken in those good old days that you can actually plot out the whole layout and put on the floor. That's like 20 years ago. And a reverse engineering will go there and check every layer of the metals and then reverse the schematic and then re-enter into the schematic editor. And this is done in the micron, 1 or 2 micron technology. Of course, now this is much more complicated as we move to advanced nodes. But there are other ways to hack the hardware system, such as side channel attack. So side channel attack aimed at extract security, extract secret from the chip or the system through the measurement of analysis of physical parameters. The example of such a parameter including supply current, execution time, electronic magnetic emission, power analysis. Consider the power consumptions when you're processing, when the chip is running, and look at the waveform data and computation steps to extract information. For example, this is a ISA crypto phase for different operations that can be distinguished by looking at the power consumption. And you see the left peak shows the power consumption during a squaring only steps, and the right one peaks showing the operation multiplication steps. That allows exponents bits 0 and 1 to be distinguished through reading the power curve. And that can be used to sabotage, espionage, and other purpose. Also, malicious hardware is sometimes referred as a hardware Trojan. This malicious modification of the circuitry of the IC or electronic system increase the need to be careful when you purchase equipment from a non-repeatable source that could have been placed hardware Trojan inside the chip or the system to leak the keyboard password or provide remote unauthorized access. So it's very difficult to confirm. But the May 2008 IEEE Spectrum magazine had an article described military radar failure due to the backdoor that was hidden in irregular commercial processors. A supply chain attack seeks to damage an organization by targeting a less secure element in the whole supply chain network. A supply chain attack can occur in any industry, not just our semiconductor. But for us, it is anywhere from manufacturing the chip to packaging to assembly and even to distribution. And that usually provide a lot of economic gain for the attackers by having an edge against the competitors. Here's an example, a various attack can happen in a typical semiconductor supply chain. IP theft happens early in the development life cycle. Reverse engineering, probably after we think the IP has been safeguarded, right? And finally, the whole lack of security measure can lead into financial losses and even sabotage the whole system. So here's a few more headlines showing the breadth of the hackers' landscape. Medical record, personal data, law enforcement target, focus on economic gain. A few examples of how much one security vulnerability can cost you: over $8 million, loss of trust, if not counted. So that is really why there are hardware hacks and why we need to come up with a solution that what we call zero trust security model. It's really think about the way that we design product today, over the internet, using the internet, using external human resources in many countries around the world. It is hard to vet all aspects of your development process. So when security is at the utmost importance, we must establish a framework and showing here zero trust model, which is to say trust no one, both inside and outside of the network. Use visibility, analytics, and automation to monitor assets and to keep the police policies in check. Remember, we're trying to prevent cloning, overbuild, parts recycling, and we want to prevent or at least detect the unauthorized insertion post-design. We also want to prevent and detect corruption inside the building the back doors and side channels, as we described, to leak information after shipping. The ideal situation is that if the supply chain can be completely untrusted without compromising trustworthiness of a chip produced. And let's take this model and look at the, SoC. By the way, here is showing the DARPA ACE program. So we started like almost a year ago, and look at the, the area. We are very proud. Synopsys is very proud to take a leadership roles in the security by working with all the players. Let's see listed on the screen. And today, Mark will do more dive on technical side of the ACE program. Really, if you look at the high level, the security goal we try to achieve is to enabling creation of a threat-resistant design that's configurable with different security level, and it's very easy to implement with the regular commercial tool. Have comprehensive coverage on formal analysis, IPs, and flows with high level degree of automation. Threat resistant design really is talk about IP, SoC, protection against reverse engineering, side channel attack, templing, and other insecure supply chain that we just discussed. The configurable security level is really try to set out the protection based on the level of security so that we have a good trade-off against power, performance, and area. Ease of use is really to take the commercial tool flow and on top of it, augment it with secure IP, repository, and some plugins so that design engineer does not learn a completely new set for security purpose. And then the comprehensiveness is really talk about the coverage on formal leakage analysis, security IP portfolio, including root of trust, crypto. I'm going to go a little bit deeper on this, fault injection on this in my next couple slides. So really, we have to, be innovate in the security engine, security SoC generator, and cost analysis. Together, optimize with power, area, speed, the regular parameters we use to do IC design. And with that we can impact the multidimensional cost function in our automation and optimization. And here is, a typical silicon. Of course, it's a simplified one with CPUs, GPUs, a system bus, and some sort of memory. So if you have that system, usually means the SoC subsystem is completely trusted. You trusted that SOC interconnect fabrics, the bus, serve the role of all the trusted network inside this whole package. That's what we usually do. But with ACE, what we like to do is that SOC need to incorporate root of trust and secure enclaved subsystem. So you're basically not trusting the CPU to authenticate the bootstrap process by itself. So submodules, entities are assessed and access control before enable the full, fulfill the primary end user's function. So with the ACE program initiative from DARPA, the new access of the security is added into optimization target. And that is PASS matrix is all about. And furthermore, on top of the root of trust functionality, we can layer on a security bootstrap and a storage and cryptographic key. So you have a secure debug and test access, and the ability to perform secure update to software and firmware. Now you added runtime access control policy, detection of the aberrant behavior, measurement, attestation of subsystem state, and now you'll really be able to detect a hack. So incorporate the measures to enable SOC capability and provide that identification and authentication. Now the device can have limit access to only certified clients. And more than that, we add a firewall allows the static and dynamic policy limits on the subsystem connectivity with the SOC, as you see along the bus. This control, including such as IO access filters to limit the subsystem communications, attaining certain operation states, MPUs, MMUs. IO MMUs can provide limits on access to memory address range and multi-range encryption, authentication of external and shared memory, provide one additional layer of security. So the ability to monitor behaviors like power level, reset event, bus traffic can further augment the security in a zero trust environment. Furthermore, we added analytics to the mix, and now you can detect a device that is compromised or fully off the rail. So really, with all these newly added elements, you need a set of tool and infrastructure to go together and work for this mutual benefit of this product. And then that tool has to be started at the lowest level when the design process started. And that is design for security solution. So we look at the aspect, logic locking, which locks the circuit enabled by a key, but does not necessarily hide the structure of the design. So people can see the structure. It might split the design into, to prevent the complete functionality until the key is provided. Now the logic obfuscation will hide the structure of the circuit. It does increase the difficulty of certain kind of attack, but does not necessarily defeat it, the attack. Logic encryption is a combination of both logic obfuscation and locking. So by combining, you prevent the chips from the functional correctness without a proper description key. So it's one layer more secure. And watermarking is latent circuitry that can be remotely triggered to produce a device authenticator. Such as sending a special string of bits would produce the watermark, which could then be used to validate the provenance. So, give a quick example. This is a historically how you integrate the DFT structure without really thinking about security. But as you see that, the DFT is where the hackers can use the scan chain to hack. So that nowadays the DFT, we had a compression insertion, right? A big decomposer on the front end is fed by a few scan input. And then the back end had a compactor, which feeds a few scan out. The input of this kind of codec is typically either MUX or XORs, and the output is usually XOR gates. And this gives some sort of amount of extra protection. But still, the hackers can glean information even with that level of obfuscation. So logic-based use a compression scheme that leverage LFSRs for the scan data input based on, the seeds and the MISRs at the back end. So this is further increase the level of protection, but still not enough. So now, because your core need to connect it into the DFT fabric, which flow the core to core, die to die, even, finally come out to a global access point, such as here, a high bandwidth access point to the testers. And that gives the full access for the entire spectrum of threats. And the bad actors outside of your chip have, a chance to get into all secrets inside your package. So more protection is really needed. And the ACE program will have more details to talk about how these protections inserted, such as, give one example here. As you see that with enhancement and the DFTs, that you can increase another level of diagnosing the hackers.
Hey, Brandon, so I need you to conclude your talk in 1 minute.
Okay, I'll skip this obfuscation locking and optimizing. So what I try to show here is on top is really the RTL to GDS2 design flow, right? So with the ACE program, we'll be able to insert security implementation within the tool. So the designer does not need to be the security expert in order to do a secure silicon design. And that itself is more secure method because now you don't have to be exposed the security method to an average designer. So that is where the ACE, the automation added the value to security. And that including also the coverage, design coverage. And finally, the test. The test you see here is that the silicon, how the silicon, when it connect to the tester, need to be secured. So with this, I will introduce the Synopsys have this silicon lifecycle management platform, okay, which is ultimately on top of ACE. It is a broader way to look at how that you can be cover the entire life cycle of the parts from security, reliability, and safety point of view. And this is exactly the premise that behind the Synopsys Silicon Life Management Platform. Because we cannot just stop in a security design, it will extend it, the whole thing, to monitor the health of the system or silicon across all phases of life cycle from manufacturing even to the in-field operation. They are optimization opportunity for all phases of the silicon lifecycle, and capitalizing on this opportunity to require some tight feedback loops between the chip instrument and the cloud-based data analytical. You will definitely see more coming through the use of this embedded monitor and sensor, the intelligence embedded throughout the entire chip, the data analytical added. This really will give specifically on-chip security, this critical element to ensure that you have authorized access to the data and a target analytical to enhance the security measurement and ultimately enable the preemptive actions. As shown here, this is using the data to find a anomalistic device behavior, such as some sort of high frequency reset, unexpected current variation, all these things. That now suddenly with the data that you can, with the analytical capability, can further increase the secure level. And for that, you'll see that in this 5 area the Synopsys business is running, that all of them have security initiatives, right? From software, verification, IP, design, and silicon. And each of the individual components and subsystem design to work together so that we can create a scalable security engine in the middle of the SoC. And we have a programmable root of trust component to implement policy, core security function like system secure boots, secure storage, and key management. We have protocol aware, crypto, interface encryptions, and we will support all the firmwares for root of trust and host. And then we will give an example in this security IPs like critical blocks, security engines that will have the formal analysis to look at the data path leakage and data integrity. The other aspect is attacker may attempt to derive secret keys used in encryption by injection like a faults that can introduce temporary malfunction during the device operation. So our device needs to be resilient to such a fault attack. So as you see on the screen that we have fault simulation engine, right? For such a malicious fault and be able to handle this attack by model using this, the fault simulator as part of your design and verification process. So with that, I complete the whole picture of the 6 topics I like to cover, from silicon to software. We had really building a comprehensive security portfolios from silicon to software, not only limited to the hardware security. So really, Synopsys has really this security initiative as a strategic initiative within Synopsys. And we definitely like to work with our customer, our partners, and also the academia together to make it successful. And before I close, I would like to mention that Synopsys is very proud to be closely connected to the academic community and IEEE, right? So we sponsoring academic event recently, ICCAT, ACM, and recently we just sponsored the CASE COVID-19 student design competition. But more importantly, we really partner with the research communities. I call the research collaboration with the leading academic researchers, professors, research institute scientists, and that partnership is very important for us to look at strategic initiatives such as security, as we discussed here today.
Thanks, Brandon.
Thank you. Thank you.
Very nice talk. When Brandon first introduced the PASS metric, I thought that's all about the talk. And then later I realized it's only one of the 6 topics he would cover. Very much information. So given that we are kind of running a bit late, I would suggest people ask a question through the Q&A session. Brandon, I think you are still with us until the end of the panel. We have another centralized Q&A session at that time. So please feel free to ask a question during the Q&A session. And also you type in your question so that I hope Brandon can answer those questions. Okay, so that's the thing. And now we move to the next speaker, Mark Terranopoulos. Mark, can you share your slides? Okay, great, we have that.
Yep.
Okay. So Mark is the director of the FIX at UF, and I can't remember how many centers he is leading now. He seems director of the directors. And like other panelists, he is one of the lead hardware security experts in this area. So Mark, you have 20 minutes and 5 minutes Q&A session.
Sounds good. Thanks. Thanks to you for the introduction. Can you hear me?
Yes.
All right. Well, Brandon did a good job of introducing ACE program. So that perhaps helps me to skip some details and hopefully meet that 22 minute requirement. I do have quite a few slides, but I may go a bit fast. So the program that DARPA ran just about a few months ago, as Brandon mentioned, this started it more than a year ago, and obviously regular DARPA programs, from developing the program all the way to the competition, and then we teamed up with Synopsys as prime, and we basically contributed to the proposal, and then obviously this thankfully got accepted, and couldn't be happier working with Synopsys folks. It's been a terrific collaboration so far. We're really just few months right now into the program execution. However, I really think it feels like a lot longer, just because we've had this sort of conversation with Synopsys for quite some time now. So the program name is ACE, and program manager is Serge Leaf. So at a high level, ACE stands for Automatic Implementation of Secure Silicon. There are 2 major technical areas within this program. TA1, called Security Systems and Tools, which really focuses on development of tools, methodologies, IPs, etc. With the pass metric that Brandon described earlier. And the second TA focuses on rapid platform development with security in mind. There are 4 major attack surfaces, particularly mentioned, in fact, in the proposal, in the program: side channel, reverse engineering, supply chain, malicious hardware. Again, Brandon described them very well, so I'm going to skip those details. The program really can be divided into 4 or 5 really entities. One would be that designers, where the designers are going to rely on a secure cloud with everything supposedly is going to be automated, with pass metric in mind. And they're going to do their design, and the design is going to go through the regular fabrication process. Once fabricated, the chip is going to be tested. Brandon again covered quite a bit of that aspect as well. And the test should be done in a secure manner. Supply chain issue starts from foundry. And the life cycle that Brandon mentioned is really an important component of ACE program. in a sense, it focuses on ensuring the enrollment is done at the fab. And from there on, the chip can always be authenticated through an asset management infrastructure where the chips and the systems can be fully authenticated throughout their lifecycle. So there's too much information in this slide. This describes pretty much everything ACE program is about, and the ones that were marked as orange are the ones that are led by FIX research. There's, I believe, 7 professors involved and a large group of students involved in this project. And on behalf of FIX Institute, and we cover various topics. Security engine is actually a major component of what we do to develop security engine statically in phase 1, configurable in phase 2, and generator based in phase 3, where you just simply input your pass metric or pass values, and then the tool automatically generate an IP optimized for PASS, and the last S stands for security. There are other important components. On the on-chip, we have watermark verification or watermark generation and verification. We have on-chip AMI support. Security IPs of different types have to be developed. Provisioning have to be done. We also spend quite a bit of time on developing this on-chip AMI to securely communicate with cloud AMI. We work with Synopsys also on developing secure communication from fab floor all the way to cloud and AMI for the purpose of enrollment and chip personalization and so on and so forth. Task 2 focuses pretty much on platform, rapid platform development with, again, pass metric. And obviously, Synopsys has quite a bit of technologies there. So our contribution in task 2 is less. However, our focus is on security estimation and measurement, where the optimization at platform level has to be done with PAS, with that additional SS security, with the attack surfaces that were targeted by DARPA ACE program. And this slide basically talk about the interaction that exists between TA1 and TA2. Everything marked in blue are done by FIX team members. And this is done mainly in collaboration with Synopsys at this point between FIX and Synopsys, even though Synopsys does have other universities that they collaborate with on other topic areas, whether it's obfuscation or other topics. And this tells you that there is quite a bit of back and forth between different team members, between different TAs, and between FIX and Synopsys. So just to give you a bit of an example and deep dive into what we're trying to do. So I'm gonna talk about security engine, but also some other topic very quickly. So in terms of security engine, the objective is to have this engine to be part of the overall platform to communicate with different IPs, memory blocks, IO interfaces, MMUs, IO control units, as well as other security IPs. And that includes watermark generations, obfuscation units, crypto cores, odometer, POF, TRNG, and so on and so forth. So in summary, security engine should provide fundamental security support, not only to the host device, but also to the AMI, so that it can enable lifecycle integrity and security. It provides secure boot, self-authentication, key generation, certificate management, IC provisioning at different stages, mainly starting from fab floor, supports security IPs, getting access to the security IPs, etc. Another important functionality is communicating through on-chip AMI and host processor to cloud AMI. And the last one is to not only monitor security properties within the device, but also enforce security properties. Just to show you some examples, we developed the security engine with two items in mind. One is the functionalities, and the other one is the IPs needed to support those functionalities. So give you a few examples. For example, key management means key generation, key storage, key expiration, having the PKI communication as well as secure key transfer. And for that, we do require IPs such as PUF, TRNG, PKI hardware, as well as secure storage. In terms of authentication and chip personalization, we have watermark for the proof of authorship, IC identification, and for that we require PUF and secure storage. A few more examples: monitoring of security policies and rules. That requires accessing trace buffers, placing hardware monitors, new type of hardware monitors, debug interface, and secure interface. In terms of security enforcement, which is more of a dynamic security property enforcement, that requires sandboxing each IP core. Brandon tossed the term firewall. It's similar to what we're trying to do as well from the access standpoint. And once you get access to each IP core, you can monitor the activities and then provide monitoring as well as the enforcement to security properties. And if you're able to reconfigure properties, then you would be able to dynamically actually add new properties to be checked. And that is quite useful when you think about zero-day attacks. So we're looking into, it's not part of actually ACE, but outside of ACE, we've been looking into how to combine this with eFPGA and then synthesis properties within the eFPGA. Encryption and decryption, AES, DES, hash, RSA, quite few actually security IPs that are planned to be developed. The obfuscation is done also by SE security engine, and that does require key management. There's a number of IPs that are obfuscated, so and the key has to be managed, but also the obfuscation during secure boot is managed by security engine. Provisioning, as well as self-authentication, self-test, mentioned by Brandon again, and so on and so forth. So there is this additional functionalities and IPs. I have quite a few slides actually to show you how the entire infrastructure works, but probably have to skip a few of them because of lack of time. But just take this PUF plus AMI-based authentication as an example where at any point in time, the device is being asked to authenticate itself. So AMI is going to send a request to the chip, ask for the authenticity of the chip, and the chip basically is going to have to first verify whether the request is legit. And once proved that the request is coming from a legitimate AMI, then it sends its ESET information, then AMI looks into the database under the ESET, identify a set of challenges. The challenges go to the chip up security engine applies them to PUF, and so on and so forth. So this is a process we put in place as an example, how a security engine through on-chip AMI through a host server communicates with a cloud AMI to be able to enable authentication at any point in time. Similar analysis could be done for on-demand key generation, key retirement, cryptographic support where encryption is needed internally from an IP, and this request again is processed all through security engine, and then the encryption is granted, and so on and so forth. Focusing on now more on the on-chip AMI within the infrastructure, as I said, is an important component for us because it enables all the communications to host processor, to the outside world, where the security is all managed by the security engine. And the idea behind it is to establish this platform to be integrated well within the SE and establish what we call a forward trust, which I'm going to elaborate a bit further. And that starts from Foundry floor, where this could be done directly by the chip or by adding a, let's say, hardware security module. And that is responsible for provisioning, enrollment, authentication, device lifecycle identification, and lifecycle management, even all the way through system retirement. And supports all sorts of functionalities, watermark verification, locking verification, key provisioning, authentication, identification, and so on and so forth. In addition to all of that, it also helps enable what we call them secure split tests, where the Foundry will not be able to call whether a certain chips is a go or no go. Rather, this responsibility falls onto AMI. So this way, you can also control overproduction, cloning, and all sorts of other potential threats. So in terms of establishing forward trust, this is a cooperation between system integrator and third-party IP vendors. In this case, we consider them both to be almost the same because Synopsys offers pretty much every IP that is needed. And the idea behind it is that the system integrator is going to have to put in the right hooks in place so that it will control what's being fabricated, what goes out of the Foundry, and what's being unlocked, and so on and so forth. So it brings in a lot of different technologies together. It brings the logic locking, scan locking, and crypto core, PKI infrastructure, communication between the two entities, in this case, SoC designer and Foundry, and so on and so forth. And this allows to be able to generate, for us, to be able to generate keys that is developed or generated cooperatively between the party IP vendors and the SoC designers together to be able to give the right key as an unlocking key to the Foundry. Of course, are all protected and communicated through that secure channel. Now, the secure channel basically, we established the direct communication between the chip through a host and AMI, but it could be done using hardware security module. And we're in the discussion with Synopsys to explore both scenarios and then to see whether we can eliminate some potential man-in-the-middle attack using testers, as Brandon described earlier, by placing, for example, a hardware security module that perform majority of the communication to AMI. There are other activities within the ACE project that Fix is working with. One is also the development of security IPs. There's about 10 to 12 different type of security IPs that are envisioned to be developed. These IPs are generated statically at phase 1, and they become configurable with pass optimized in phase 2. And then there will be generators in phase 3, where all you need to do is to enter your pass values, and then the tool automatically generate an IP optimized based on that metric. There are, as I said, a number of IPs, but maybe a slide on the odometer as an example, boot odometer that the team is developing, which takes advantage of existing non-volatile memories or anti-fuses, and then uses different things as a trigger. It could be a clock, it could be a power on switch, etc., to be able to measure how many times the chip has been powered on to represent the usage of the chip. Or some of the earlier work that our team has done on odometer, where we take advantage of aging that exists between different ring oscillators by keeping one as a stressed and the other one as reference ring oscillator, and then difference between the two represent the aging, right? Another important task within the group is security estimation and measurement. This is probably one of the most least researched tasks not only within the group, but also within the community, because metrics have been a challenge for security community for all the good reasons. One is obviously having consensus on the metrics is difficult because different groups and different researchers with different skill set and expertise, they view metric differently, right? So it's good to have this sort of community-wide discussion around metrics so that we can have some level of consensus. So around that, and the metrics we're looking at it in ACE program focuses both IP level metrics as well as platform level. And what makes platform level is interesting is that once the IP goes into the platform level, suddenly there is so many other parameters that we need to consider. So looking at the time, I need to skip some details, but provide you with an example. Let's say we take a IP with certain security measures against power side channel, reverse engineering, malicious hardware, supply chain. Individual groups within the ACE team are actually developing metrics for each and every one of these vulnerabilities. Taking that IP level security and then use them for the optimization and for the IP itself, then take them into the SOC, and then from there, try to calculate what the SOC level security would be as a challenge. So let's take power side channel as an example. The power side channel at the IP level, there's tremendous amount of work, especially post-silicon, but we've been doing quite a bit of work at the pre-silicon power side channel measurement, and that's RTL level and gate level. But if you do the measurement at the RTL level, even with the assumption that you do have some good correlation with the silicon, the moment you take that into an SOC, then there's so many other parameters that kick in. So this table actually talks about what other parameters kick in when you transfer your IP into SOC that is start to impact the metric. And what we're trying to do is to understand what those parameters are. And considering that ACE is focused only at RTL, many of these parameters, they actually start to come in later in the design stage. But what we're doing is we're taking a specification into account and try to adjust the security level based on what we get. This is all estimation, by the way. There is also effort for security measurement where you have to apply real workload and then run the simulation for a long period of time and then do some sort of a correlation analysis between what you estimated as a security and what you estimate as what you measure as real security. And there's so when it comes to power side channel, for example, you have the on-chip voltage regulators, dynamic voltage frequency scaling, clock jitters, all sorts of glitches, workload. There's also this spatial and temporal effect that comes from other IPs around your IP, decaps, and so on and so forth. So I can go on and on for all of these parameters that impact your score or metric value that you get from the IP level side channel. Another big effort in the team is focused on watermarking, which provides proof of authorship. And again, the technology has to be developed, and what we're doing, we're mostly focusing at this point at the RTL level, finite state machine, don't cares, etc., to be able to develop watermarks. That these are watermarks that when they go from one stage to another, they should not, the translation should not impact the quality of the watermark. And I'm going to skip the details. Another one also focuses on security IPs that are being developed and then how you integrate them with the SE, and then within all the IPs that we have in the SOC, that is focuses on providing sandboxing solutions to the IPs, firewall concepts that Brandon mentioned earlier, and hardware IP management module. Again, all with enforcement and monitoring capability for security properties, again, with pass metric in mind. So just to conclude this, the architecture community over the past 2 decades or so has spent quite a bit of time on providing great set of solutions. And majority of them actually, they transfer and translate well when we go into the integration step, but some they don't. So understanding what actually happens within the integration phase is important. And the fact that new attack surfaces also are considered during the SOC integration that makes this a bit more challenging. So the key to ACE program is automation, automation, and automation. And this is really, as Brandon mentioned earlier, to reduce the total cost of security by trying to enable existing tools. We're not changing what Synopsys does. We're trying to add on a script around what Synopsys does best. So that helps with bringing the last S into the parameter, into the metrics, and perform optimization by keeping that as well. And we all know that this is a trade-off between power, area, and security. And ACE is basically a program that brings the EDA, the academic, as well as defense industrial base together to establish security metrics, tools, and IPs to address all of these vulnerabilities. Of course, the focus is on 4 of the vulnerabilities or 4 of attack surfaces, but we all know that there's a lot more attack surfaces involved, but DARPA decided that these are the 4 that they're going to focus on. So that ends my presentation. Try to my best year to go as fast as I could. So hopefully.
So actually, I was about to ask you to conclude, and you are already on the final conclusion slide. So I guess there are many questions regarding the ACE program, regarding the overall data center style thing. But in order to stick to our schedule, I would postpone the Q&A to the final Q&A session. So thanks to Mark again. And our third speaker is Gangku. So Gangku is one of the dedicated hardware security educator. Many of you may take his MOOC course online. So including myself, I really appreciate his effort in promoting hardware security through this educational part. Gangku, can you share your slides?
Yes.
Okay. So again, in order to stick our schedule, I would ask you to kind of conclude that in 20 to 20 minutes. Yes, thank you.
Okay, so I'm scheduled to finish at 11:26. Okay.
Okay, that'd be great.
And first, thanks IEEE CEDA and ACM SIGDA, thank Ira and Zhongyi to, give this opportunity. So for us to talk with the audience, with, people, friends all over the world about this, this effort we're having now, okay? So I give this title, Assessment of Hardware Security and Trust. That is because when Ira and Zhongyi contact me, they want me to introduce about our role in the DARPA ACE program. So as I was, talking, very next, couple of slides, and our role is in some sense the assessment. So that is why I give this title, and then that is also something, I'm just started learning. And I thank, Brandon and Mark to give, some nice introduction about the DARPA ACE program. So I can probably, really fast forward the first couple of slides. So this is a slide I got from Sergey and Sergey, who is the program manager for the DARPA ACE program. And the goal of the program is trying to automate inclusion of the scalable defense mechanisms into chip designs to enable security versus economics optimizations. And I think, both Brandon and Mark has, they have stated this one very, very clearly. So it is about the automated implementation of security for silicons. And this is another slide from DARPA's program where they mentioned about the 2 technical areas, which I think Mark mentioned about TA1. So let me try this. So they separate the TA1 here and the TA1 here. So this is more or less about, the current research or the existing research about all the hardware security and trust features. And this one talks about more or less the implementation part. And the TA2 here is focused on the integration. So the basic idea about here is they focus on these 2 words, AI, which is not the artificial intelligence. It is the one we call, automated implementation. So the key here is, I think, the message also you get it clearly from Brandon and Mark is not trying to develop a lot of new techniques. It is about trying to commercialize or trying to, in some sense, implement the existing research from the research community in the past, 2 decades. And these are the 4 specific, focus areas, which I think Mark has showed it a couple of times. There are side channels, reverse engineering, supply chain, and malicious hardware. And the DARPA actually, they have 2 teams working on this project. And the first project is, the first team is the team Synopsys, led by Synopsys with a couple of other companies, Boeing and Ultrasonic, which are the 2 leading IP providers. And also there are University of Florida, Mark and his friends, and Texas A&M, University of California, San Diego. So 3 universities are involved. And the other team is led by this company called Northrop Grumman, and they have IBM, University of Arkansas, and University of Florida involved. And they are only working on TA1. And so then what is the role of our team here in University of Maryland? So we was approached by DARPA earlier this year, and then they formed this team called IV&V team. And the key purpose for us is to do the assessment. And our team mainly consists of researchers from Maryland and NYU, the New York University. And this Fraunhofer is an institution that is a German-owned research institution, which is located in College Park, in University of Maryland. And these people are also, in some sense, either our faculty members or affiliated with us. So to be more specific, so what we do in the DARPA ACE program. So basically, this is the scope, which is, I got the slides from the kickoff meeting of the DARPA ACE program. So what we do is we do the assessment, and this you have this 7 bullets here. So the last 4 are the 4 technical areas. So these are talking about more on the system integration part. And it is, so ideally the ACE program is going to provide an automated chip design and implementation platform, which will be available on the cloud. So people can use that automation platform to do the design. And what is new in that platform is security will be integrated as another design matrix, together with chip area, with the power, with the speed, with all manufacturabilities, with the testabilities, with all the traditional design objectives. And I'm not going to read all the details about, in particular, these 4 technical areas, because Mark and Brandon, they have done a really great job in explaining these 4 areas. So what I'll do is I'll try to, use the next, 12, 13 minutes to give you some sense about what we are going to do, or in some sense, what do we mean by hardware security and trust? And given the time I have, I probably will focus on this one small example, which is people, talk about the finite state machine model. So this is a small question that most of the people, when we do the digital design 101, we know that. So we're going to design a system that is going to implement, which sometimes people call the pattern generator or the pattern recognizer. So you are going to recognize, in some sense, for example, 5 letters with a pattern of 5 objects. And then they can be represented in this case, for example, 0, 1, 3, 5, 7. And this pattern will show up repeatedly, one after another. And this is represented by this thing which people call finite state machine, where you have 5 states: 0, state 1, state 3, state 5, and state 7, and then you go back to 0. And this is another representation of the state machine, which is the one we call, the state transition table. So these are the states, these are the flip-flops that we implement each of the states. And this will be their next states when you do the transition. And when we do the typical design, I'm going to skip all these things here and then show you the design here, okay? So this is the design eventually we have, where we implement this using 3 T flip-flops. So the flip-flop A, flip-flop B, flip-flop C. okay? And this is in some sense, I mean, for regular, I mean, undergraduate students who are taking the digital logical design course. So this is in some sense, this will be the perfect answer here. So the system here does provide you this functionality here. So it gives you this repeated pattern of 0, 1, 3, 5, 7, and then go back to 0, and then keep on repeating there forever, okay? And for people who are doing testing, we know that for this design, there's another very important aspect you have to test, you have to check. And that is something people call the self-correcting. So what is the meaning of self-correcting? So let's go back here. You see, okay, so if the system with these 3 flip-flops, A, B, C, and I'm implementing these 7 states, 0, 1, 3, 5, and 7. But there are 3 other states, 2, 4, and 6. They're not specified here. So in my design, I don't really care about, I mean, what will be the content for the flip-flops during that time, what will be their next state, the transitions. However, now I have this true implementation here, the hard piece, the physical system here. So I'm going to take a look, and then I'm going to check what happens if, for example, at state 0, 1, 0, when the input here, when the data here is 0, data here is 1, data is here. And then I'm going to let the clock run 1 clock cycle, and I'm going to come back and check what is the content for these 3 flip-flops. So let these people talk about, I mean, you check whether this thing is self-correcting. So if for some reason you run into this unexpected stage, so what will be the next stage? So this is in some sense when we get out, and then when we to figure out all the flip-flop content, and then we try to figure out what is the next stage, okay? So in this example, from state 2, it will move to stage 5. Because for example, the first bit A, it is going to be toggled because this is 1. So it changes from 0 to 1. And so now let's come back to the final state machine level. So this is the initial state machine we're supposed to implement. And after I've done this circuit analysis, I know for the other 3 states that are not specified here, I know what will be their next stage. So I'm going to add this to the final state machine, okay? So now I have a complete final state machine with all the 8 states. And for each of these 3 unwanted states, their next move will go back to this circle, which in that sense, we are saying this circuit is self-correcting, which means that if for whatever reason you come up with a wrong state, with an unspecified state, just let the clock run 1 cycle and then you come back to the right track. So this is a very good design. And so what happens now is we see, okay, so we are done this, and this is probably, I mean, for some advanced digital logical course, you can tell the students to do a self-correcting. And how does this connect it to security and trust? So what I have here is, I have this original one, the state machine with 8 states. And somehow if I do the test and I come up with a different design, and if this is what happens with the 3 unspecified states. And in this case, you see, I mean, if you come to 6, next time you go to 4, and the next time you go to 2, and then next clock cycle you come to 4, and then you're going to remain here as a loop. So this is not self-correcting. So the design is not well-defined, the design here. So these are the things that in the traditional design we're trying to avoid. But now with one of the features, for example, Mark mentioned about, I mean, the watermark. So now if I do the circuit, I mean, if I try to test the circuit, I check the final state machine, and I come up with this state machine here. And I say, okay, I still have this pattern here, which does the 4-state transition here. And for each of these 3 unwanted states, they move into the circle. So they are self-correcting, and which in some sense, it is a good design. This, again, it is the same, it is a good design because eventually they all move back to the circle. And however, what we talk about the security here is, for example, in the ACE program, that's when their team decided to add a watermark based on whatever their mechanism, and eventually come up with this. So then the thing here is, I mean, I should be able to verify that, okay, in some sense, they designed this transition, not just randomly. In some sense, they want this transition to happen, in some sense, to reflect their watermark. So that is in some sense one of the objectives for us to do the assessment. And I give you another example here. So again, I mean, I have finite state machines. So now I have two state machines here. So the first one here, it has three states, 0, 0, 0, 1, and 1, 0. The second one here, it has four states. And I ask you a very simple question. Are these two finite state machines the same? So of course, this problem is probably not well defined. So what do you mean by the same? So of course, if you take a look, and they look different because this one has three states and state machine 2 has four states. And you can say, okay, so they're different. And how about if I say, okay, so I ask, are they functionally equivalent? So this is for most of the graduate level logical synthesis course, they are going to discuss this. And to check whether two state machines, they are functional equivalent, you have a formal method, which is called product machine. And then if you build a product machine, you can indeed verify that indeed these two state machines, they are equivalent. Assume that this is our initial state. This is also the initial state. And you see in the state machine 2 and all the dark edges, the black edges, they're the same as the state machine 1. And the red edges, they're the new edges, okay? Okay, so as a matter of fact, so how do we reach, the second state machine? So that is I start from the state machine 1 and I do the traditional system design, and then eventually I come up with this digital circuit. And then when I do the finite state machine a representation of this circuit with a full circuit analysis, I come up with this one here, okay? So that is basically shows I have a correct design. And then if you use the product machine to verify this, they are the same. But what are the security concerns here, or the trust concerns here? So imagine this is your initial state. This is also the initial state. So if you take a look at the original state machine, so once you leave here, you can never come back to restart. There's no incoming edges to this state. So you cannot come back. So restart is not an option for this system. But in this case, you say, okay, state 0, 0, which is my initial state, I can go to the restart state from any of the other states. Then from that aspect, so these two states, they're different. And this one has this additional feature that you can go back, you can restart. And if you want to think about the security, if this is the state that people want to have access control, so people cannot come to here, but in this design, everybody has the permission to go there. So that is not good. And so hopefully, what I'm trying to convince you from this slide is, so there are a lot of things you need to test, you need to assess, you need to verify beyond the traditional design objectives when you talk about hardware security and the trust features. In particular, as the ACE project they are going to do is, they are going to embed or implement the existing security, hardware security algorithms or approaches which we have developed in the past 20 years into the EDA tools. So I'm going to quickly show a couple of other examples. So this is a digital watermark example where we implement the DES, that is, this is more than 20 years ago, and on an FPGA board. And this is the one without watermark. This is the one with watermark. And visually you can see some difference, but the things here, the things, how can you, develop a tool in some sense, do a formal assessment to show that your watermark is indeed there, is indeed robust. And this is another example here, which shows this concept called the fingerprint. So if I, for example, at the gate level of the IP of the circuit, I see these two things here. And I'm going to see, okay, so they look different, but if you do an analysis, they have the same functionality. And then why we are doing that? And then you have to make sure that when you do the design, the optimization tools is not going to, in some sense, remove this one, okay? Because this one has been put here for a purpose, which is trying to embed your fingerprint. And the last example I'm going to have here is, so we talk about the logical obfuscation, or where you have the designs that looks different, or in some sense it is hard for any reverse engineering attackers to analyze. So what I have here is, I have some, transistor level, logical gates, and it is not clear to us what these are. But if you go to a HSpice simulation, you probably can see, okay, so what will be the input output, I mean, the truth table. And then you can conclude what are the functionalities. And indeed, these are something we call, I mean, polymorphic gates, which means that the gate will behave differently if you change the operating environment, for example, the temperature or the voltage. And in this case, we change the voltage. And with different voltage, this logical gate can be either exclusive OR gate or can be a NAND gate. And similarly, this one can either be a NAND gate or can be a NOR gate. So this increases the difficulty for people to do tests, to do verification, to do assessment. So if for some reason they decided to use polymorphic gate to do the logical obfuscation, and then we have to, in some sense, at this level, we have to go to the circuit to verify this, to show this, and also more important, to show that how can you use this to obfuscate the design. And finally, so let me conclude here. So what we have here is, so for our team, our goal is trying to do the assessment for hardware security and the features that has been embedded into the ACE program, to the automatic implementation, and what to assess. And so this, most importantly, trying to test the security and the trust features they have claimed, and also try to evaluate the trade-off in the traditional design objectives, like the power, the timing, the size, the chip area. And how do we do the assessment? And these are the things that I mean, in the earlier slides, they have more details. So of course, I mean, there should be a formal analysis, which, because I mentioned in the ACE program, it focuses on automation and implementation. So most of these features, they have been, these algorithms, they have been published before. So for all those papers, they do have analysis, security analysis. And in our approach, we are going to focus on this. So we are going to use the platform that's delivered by the two ACE teams, and then try to do some designs to simulate the design, and then try to launch certain attacks, and then trying to evaluate whether the design becomes more secure, more robust against the attacks. And finally, that is something, I mean, it is, I call it beyond assessment. So the goal here is not for us to check, I mean, whether the teams are doing a good job or not. That is one thing, but the more important, we're trying to find out whether there's new vulnerabilities. And then indeed, the ultimate goal is trying to improve the security and automation of this, I mean, ACE program. And when I talk about the finding new the unknowns, we're talking about, I mean, in the design. So whether there's any unknown, for example, vulnerabilities, which people have not identified before. Whether in these countermeasures that the two ACE teams, they have decided to implement in their, I mean, platform, whether this will introduce any new attacking surface. And also in the implementation and in the automation process, this is probably the parts that you can have a lot of new vulnerabilities. For example, we know, I mean, Mark mentioned about the power analysis. That is come from the not secure implementation of the modular exponentiations. And to conclude here, so I put, I mean, the ACE logo here back again. So we know that IC test, it is hard, although I'm not a person doing tests, I'm slowly learning it. But most of the traditional test objectives, they are well defined. And for hardware security and the trust, which have been working for many years, so we have a lot of, I mean, when I say we, I talk about the community, not our own group. So there are a lot of research results going on in the past 2 or 3 decades, but again, there are still a lot of more unknowns here. And the ACE program, we have 2 teams, and the goal here is trying to, in some sense, commercialize all this research results in the past 2 decades to product. And finally, I talk about our assessment. How do people assess or test the security features? And I talk about, I mean, our role here as the DARPA's ACE team, IV and V. And thank you very much. And I think I'm a little bit, I think 2 minutes over.
Thanks, Gang.
Okay.
Thanks. Yeah, as I mentioned, you're a good educator. Even though I know the concept, is still a very good memory refresh to better understand the FSM technique. So again, as I said, thanks for the presentation. We will keep all the questions at the end so that we can stick to our schedule. The last but not least, Ahmad. Ahmad, he is a cybersecurity experts. So, but recently he seems decided to work on hardware security. Well, we are all wondering what he would do to hardware security. He organized the Hack and Deck and Hack and Sec competition, which really like raised a lot of noise in hardware security area. I think even recently DARPA had a program called FETT, is following this style, slightly different background. So Ahmad, we look forward to your talk introducing us more about the Hack Stack, Hack Deck, or something similar.
So do you hear me?
Yes, but can you share your slide?
But no, because, okay, I share, yeah. Let me see if it's the right, let me see if it's the right one. Oh, I hope it's the right one. Let me see. Ah, yes.
I think so. We can see the slides.
Oh, that's beautiful. Okay, so now I have to somehow, yeah. So do you see now this slide?
Yes.
Okay, thank you very much for the invitation. Maybe some remarks to your introduction. First of all, I am not a member of ISIS or ASIS, how you call it, I don't know. It seems to be a very interesting project, but typically German universities are not funded by DARPA. So it's independent of that project, but I think that project has a number of interesting, as far as I understood it, a number of interesting parallels to the projects that we are doing at our university, but also with other colleagues in Asia and in US. The second thing is, I'm not doing for just since 2018 hardware security. I'm doing that for more than 20 years in embedded security. So I think that is clear from our publications.
Okay.
Just a small correction for the next time you introduce me. Since you talked about Hack and Deck, I would like to first, before I start about enclave computing on RISC-V and security containers that most of you may know or may not know, maybe I just start with something that I call the insecurity of security architectures, or the myth of trust anchors. So we always talk about trust anchors in hardware, and for many years, many security experts, including myself, when we write papers, I mean, Yair knows that, we always talk about, okay, we can trust hardware, and we consider many aspects of physical access out of scope. So I'm not talking about physical access, no electromagnetic waves, or no, so to say, hardware-oriented side channel attacks. I'm talking about you have no hardware access, and you just launch an attack remotely. So one idea, one so to say aspect on why we can't really trust on trust anchors, and how should we make these trust anchors, because it is always a relative aspect. This was a problem that attracted myself, my team, and also a number of other colleagues that maybe I can name them here during the talk. So as was mentioned by other speakers, especially the first speaker, I think Brandon from Synapses, mentioned several times side channel attacks, both in hardware and what we call software side channel attacks. And there is, of course, a religious debate among scientists, what is actually hardware side channel, what is software. Everything is side channel attacks, or everything is hardware-based side channel attacks, but we don't go there. So as you can see on this slide, there is a big buzz and big hype on microarchitectural hardware-based attacks, where I just put some of the most recent attacks from Spectre, Meltdown, CLK Screw, TL Bleed, Foreshadow. As you see, all these attacks, they have to do with microarchitectural attacks. That means mostly it's about transient executions, mostly it's about all the performance aspects that were designed in the hardware, but unfortunately, any intermediate computation is visible to software. So I'm talking about the so-called, as we call it, cross-layer exploits. That means you can remotely exploit a system by exploiting or by knowing the hardware vulnerability. So you use software, unprivileged software, to really attack a system by knowing hardware vulnerabilities. So, but our question was, as you see, there are a number of nice names here. So the title of this probably like Zombie Land and Spoiler, but many of these names are much more creative than the content of those papers. So that means, I'm just not offending anybody. Every other is interesting, but they're all the same. So the question is there anything else in the wild that we need to look for it? Because that was not very, that was a bit embarrassing for all you know, big companies, semiconductors, to have this problem in their processor because of closed source aspects. So this is where we found out, okay, all these patching aspects were not helpful. So we started with Hackattack, that I just want to make a kind of commercial here for it. It indeed started very, very small with a poster session at DAC. And now we are kind of extremely popular. And until now, more than 160 teams, each team at least 4 to 5 people. So several hundred people were trying to find the vulnerabilities or design flaws that we fabricated into the chips or SoCs in general, together with Intel. So here, Intel has really provided us with many, many insights that usually is under NDA. And because it is in their advantage, you get free labor. I mean, all the smart people all over the world are trying to hack in your system, and you don't even have to pay them. So that is a very good thing for Intel, but also for those groups who are fine. So it was so popular that even Usenix Security this year asked us to do it at Usenix as well. So we had really double of effort on Usenix and Hackattack. So if you're interested, contact me. I can give you lots of information. We are publishing more and more information about this. And also we are going to put it in the Amazon to make a Hackattack or Hackatsec as a service. Okay, so I just don't go through all the things. What is important here that there were deep dive bugs in the hardware, but the interesting point is that these vulnerabilities can be exploited by software. So they are cross-layer attacks. So they go beyond microarchitectural attacks deep in the hardware. So I'm just reporting from Hackattack 2018 and 19, just go very fast through it. We use a lot of CVEs that were existing to fabricate the bugs. And we used also bugs that were internally found by Intel, or they were never published. And some of them were revealed to us to put into this SoC. So there are lots of insight if you participate. We use RISC-V as a platform because Intel was outside. Intel would not give us the opcode, as you know. And we did a systematic analysis that the bugs were really systematically designed. So from boot ROM to memory bus, from cryptographic engines to peripheral registers and so on. So, and we considered 4 aspects: denial of service, privilege escalation, software exploitation, and leakage of information. So these were the classes of attacks that people could use. So this is a list of one of the first bugs. This was over 30 bugs. But what is interesting is that some of the teams, they could find bugs and they could find design vulnerabilities that we did not put in the open source RISC-V platform. That means they were native platform vulnerabilities that we didn't fabricate. So that is also one of the side results of this inclusion. So now I come back to the thing and make it fast because we have only 20 minutes and it's soon gone. Back to the main story, and that's enclave computing. What is enclave computing? Most of you know that. We have an abstract view of the system here. You have operating system, you have your applications, but you would like to have hardware-supported, isolated, trusted execution environment which is called enclaves, and you can run your app security. So this is the idea of enclave. The industry solutions, Intel SGX is one of the most sophisticated ones. Then we have AMD's SEV and ARM's TrustZone, which is already almost 20 years old. So, and they provide some kind of trusted execution environment, some kind of enclave, and we have seen that they were massively target of side channel attacks, mostly based on shared resources like cache-based side channel attacks. And we can today say that SGX, although side channel attacks was outside the scope of SGX, SGX has been massively attacked, and I don't know how they can come out with it without really very, very high, or let's say low performance or high load of patching, and everything must be, you know, repaired again and again instead of having a fundamental solution. So, but solutions are all requiring hardware modification. And RISC-V concept, although it is an open source, and open source doesn't mean security, it means that it is more eyes can be on it if those eyes are there. So for enclave computing, I think one of the future directions would be RISC-V. So let us see what is on the market. I am just going to select some of the works which are mostly cited in this area for security architectures, or as I call it, enclave computing on top of RISC-V. So just to have an isolated environment that is not prone to a variety of side channel attacks. I will come to that later. So this is again your architecture. You have your caches, L1, L2. You can see it here if you look at the system bus. You have your applications, then user level and supervisor level, as you know, for every systems. And in Sanctum, which is a proposal, security architectures by MIT, you have the so-called user level enclaves. So as you see, it's like a user app, user space app running on top of the operating system. So an OS manages enclave. There is a security monitor that is a high privilege, very small amount of code that manages OS, or let's say checks OS management decisions. And there is a custom circuitry, which is the memory management unit that does access control. As you see here, the enclaves A and B in hardware are completely isolated, and then they can run their security critical applications. However, the side channel protection here is implemented by using page coloring, and page coloring means that you have, let's say, enclave A in the memory, enclave B, OS, and then the part for SM. And this pattern is going to repeat, and this is, of course, not very practical because you have chunks of OS always in between. Then there is Keystone, which I think most of you know. This is on kind of on the flag of RISC-V community and foundation. And here we have another architecture. This architecture came after Sanctum. Sanctum used the first versions of RISC-V. Here, you see that you have enclave with the runtime enclave. For example, not only your application is running in an enclave, but also the drivers can be put in an enclave, which is important because drivers are source of lots of, so to say, security vulnerability. So they are in the isolated environment. And enclaves are protected by something which is called physical protection unit. Here, this is PMP. This is new compared to Sanctum, a special component that provides protection of enclaves. And if you look at, for example, one PMP region reserved for each active enclave, and then the assigns the caches or cache ways, as they call it, assigns to processor cores. Another architecture that I would like to show to you is very shortly is Timber 5, which is designed for embedded systems. It uses, again, application, so to say. It, of course, isolates sensitive part of an application, and it is at, as you say, is at user space level. And for protection of, so isolation of memory, it uses tagging. It has no caches because it is for very small systems. It has a memory protection unit, and the memory access controls are controlled by tag engine, and cache memory, as I said, does not exist. So if you put them all these three relatively new and known architectures, so enclave architectures based on RISC-V that are trying to, let's say, prevent side channel attacks, this is a kind of short comparison. So for example, they have user level enclaves, then you see that Sanctum does it have it, the others don't have it. User supervisor level enclave, this is where you can put even higher privileged, so to say, software in your enclave. In process enclave, that means within a process you can have enclaves. Dynamic cache side channel resilience, this is a typical cache side channel or control side channel resilience, which is more about the fault injection, for example, page table fault injections, or enclave to peripheral binding, which is secure IO. So none of them provide secure IO, or at least they still don't have it inside the thing. So at last slide, I come to Q. So we looked at all these architectures very thoroughly, and wanted to have something, because the problem with many of these platforms, enclave platforms, is that we need to consider applications. This is what people at Intel dropped for SGX, to my view. You cannot just start to design hardware and say, I want to solve all the problems in the world, but I have no idea what for application come on the top. That is, of course, a generic approach. I understand this. But on the other hand, there are many emerging applications, many emerging technologies that you need to take care of. So for that, you need a really clear analysis of what is pragmatic for practice. So sometimes you want to have a, so to say, an enclave at the user level. Sometimes you want to have an enclave at runtime. Sometimes you want to have an enclave which is bare metal. That means it is running directly on your hardware. So how do you do that? You need to have a very flexible, configurable system. And this is what we tried to do. And this is going to be published at Usenix Security 2021. The paper got lots of praise because actually, unfortunately, at security conferences, attack papers are more popular than constructive papers. But here, for example, this security monitor is a very small software that manages a lot of things in the system. For example, configures the so-called filter engine. So why this filter engine? We have a small amount of hardware logic on the bus system, and we have a security monitor that is anyway in all RISC-V, in the RISC-V architecture. But we can have an in-process enclave because, as you see, security monitor is a part of firmware. But I don't want this to protect the whole firmware. I just want to protect the security critical of the firmware. And this is where we can put even this security monitor, which is very high privilege, but attackers want to target it as well, because then they can get control over the whole system to protect it by means of enclave. So as you see, this filter engine on the bus with a very simple logic, provides access control to all peripheral devices. These peripheral devices can be anything. For example, an AI chip, accelerator. And then you can assign directly any enclave directly to the peripheral over a secure channel between the enclave and the peripheral. Note that in all these constructions, we are trying, or at least we are doing our best. Also, SGX claims that operating system is untrusted. So operating system could be malicious, even in the presence of malicious operating system, this channel should work. So enclaves can be assigned immediately to peripherals, and this is what the secure IO does. So this is a comparison with Cure. We call this our architecture Cure because I think it cures some of the problems of other architectures, but it is not the last word, because then we have Hackadack. If anything is, if any bug, any wrong concept is at the lower hardware level, and it can be exploited by software, this is where Hackadack comes in, and there is a big story around it, how you can really find these bugs in, because the state, there is a state explosion in hardware. If you want to check everything in hardware with automatic tools, this is a fantasy currently. To do that with tools, we need a combination of a lot of techniques to have a pragmatic and effective security. So as a conclusion, I would not go through it, just finish it. I just put it all together. And what I think as an open challenge is, so I think RISC-V is very important, I think, for research community, but also for industry to examine a lot of aspects. Also, all research proposals in the area of RISC-V, they do not ignore side channels. And as I mentioned, there are a number of sensitive services that need other kind of enclaves, and this is what this system should give them. But what is the challenge is that we still, although we have cache partitioning, we have a hard cache partitioning. That means you have really, for cache lines are devoted to enclaves, there are still more desire for efficiency of cache partitioning, which is, we are working on that, and that is an upcoming paper. And what we are working on it also with other people is enclave architectures for network on chip platforms, because I think network on chip platforms are very useful, and especially for multi-core systems, you cannot put them on the simple bus. And how to generate enclaves for this kind of architectures is the next step. Thank you very much for your attention, and I hope that
Thanks, Ahmad.
you have some questions.
Very nice work. So now I correct myself. You are both in hardware security and a cybersecurity expert. Okay, so let's open to the audience. Please feel free to send your question, either put in chat. I don't know whether you can talk, but I guess you can at least type in your question through the chat channel or through the Q&A channel. We are a bit like over time, so we have around like 5 minutes-ish for all the questions. But I assume that the SIG-DA and the CIDA would release the presentation, or the whole presentation I recorded, they will release from their website. So maybe Iran or Zhongyi can tell us more about, because I do get a question, people asking whether they can get access to these presentations, to the whole panel.
Let me say it first. Yeah, I think as for the video, we actually recorded, and after to confirm with all speakers, because maybe some speaker would not release some slide or some partial of the talk, and then we will remove it, or we will put it on the CIDA YouTube channel. Okay, thank you.
Okay, that's good. We do get one very quick question about the QR paper. Ahmad, when you would release the paper?
The paper will be online. I think the camera ready is in 1 month. So latest in 1 month, it will be online. Because we are not, we don't put it online before the camera ready. There are some comments of the reviewers that are getting, but there are not so many comments. There are 1 or 2 comments. Maybe we even can put it in earlier.
Okay, that's good. We do get a technical question. I just don't know who will be the appropriate person, but feel free to chime in for all the.
Yeah, you can answer it.
The proxy computing. So do you see any security issues in approximate computing?
So Iyer, can I answer this one?
Yeah, sure.
So because I just want to, I mean, show that I'm not just an educator. I'm also trying to do some a little bit research.
Okay.
Yes, exactly.
All the panelists are both.
And you are also not hardware security guy.
yeah, exactly. So I'm not just doing hardware security. I'm also doing security on approximate computing. So there are a lot of concerns for security issues in approximate computing. And then we're writing a big paper which will be published in the proceeding of IEEE, which we are going to evaluate what are the vulnerabilities, what are the research directions. And one of the key concerns I see from the approximate computing, the security feature is there. So when you do approximate computing, your result in some sense will have errors, will not be accurate. And then it is very hard in some sense to distinguish whether the error is introduced because of approximate computing or because of malicious modification, or by, for example, the manufacturer variations, whether just the typical fault or, I mean, errors. So that is one of the biggest concerns. And across the world, so there are a lot of people now working on approximate computing for security or security of approximate computing. And they are working on the security concerns for the approximate hardware, like the approximate adders. They're working on how approximate computing can be used, for example, to improve AI security, improve AI's privacy, and a lot of things there. So it is a very, very promising area.
Okay, thanks. Let me see if we have another question here. Is that most of the hardware security paper are related to the defense side, like a microarchitecture attack. What is your perception about offensive security on hardware, which means that from the attack side?
So shall I give an answer, or anybody else?
Yeah, I think all of you, maybe Ahmad, you can go start, or maybe Mark can go second. So just
have Ahmed go first, and I'll try to add to it.
Okay, so offensive security has been a big discussion, not only for hardware but also for software in general, on the political level first, because offensive means you can attack another system, and that system can be a friend or can be a foe. Now, and in Europe, especially in Germany, offensive systems research are not appreciated. That has historical reasons. In US, offensive systems have been used in military era, but think about the following. Offensive systems are gold mine for security researchers. Why? Because if I can hack into an offensive system, I can destroy much more. This is a very delicate point. It's exactly like artificial intelligence. This is also a gold mine for security research, because you can hack into that system and run it in a stealthy way. Classification are wrongs, you can do denial of service. So whoever does offensive security must do it very, very good. This is why I think it's nonsense. Okay, sorry.
Thank you, Mark.
Yeah, I think there's the same attitude by U.S. government as well. Generally speaking, they do not appreciate or even stronger approve offensive research. Where if offensive means you're trying to attack into somebody else's system, that's where issue comes from. But if offensive means you do an effort like Ahmed does with Hackadack, or a lot of competitions that we run, where a bunch of white hackers get together to try to assess the resilience of your security mechanisms that you put in place, actually is very much welcome. So it all depends what you mean by that offensive mechanisms. But at the end of the day, we all know defense will not exist if offensive techniques were not in place to find those vulnerabilities. So I second what Ahmed said.
Okay.
Yeah.
So can I just add one thing here? So I agree with both Amar and Mark. So offensive security is very important for hardware security research, and not just the hardware. I mean, pretty much all the security come from attacks. And the US government has a very, very strict, regulations on this. So for example, a couple of years ago, we had a project with NIST, and then trying to find some mitigations for GPS spoofing attack. And then when we try to do this, do the experiment, the GPS spoofing, you cannot do it in your university lab. You have to have a dedicated facility to do that, because otherwise the GPS spoofing may affect some other devices which are close to you that they are using the GPS signals. So it could cause a lot of damages. So if you're just for research purpose, so it is welcome, but you have to be very, very careful.
I see.
Yes.
I guess there are some, not just a technical question here. So there's another question coming in is actually for Brandon. So Brandon, can you hear us?
Yes, sorry, I mute myself. I was talking without the microphone.
So the question is about you mentioned actually in the slide that you've been like sponsoring a lot of events. The question would be how to approach Synopsys so that they would get support for some other events. Like what will be the channel? Is that
yes. Patrick Haspel in my group is the director for APOP, means Academic Partnership and University Program. Yeah, definitely he's one channel to reach out. Even at the Synopsys website, there's a link to university program academic research, but you're definitely welcome to connect with me or Patrick directly. We're more than happy to connect with, with the academic community.
Okay, so this is for more like a sponsorship to events. Is there similar for kind of like a research project wise?
Yes, so there's three types of things that we engage. One is the sponsorship to the events, right? And that is to really broader communities, not only, with the specific research area, but anybody that doing electrical engineering could be really be user of our Synopsys tool or IP, and that's why we sponsored this event as a branding effort. Now, the engagement with particular research professor, of course, is much more selected. That once we have identified the area of interest, we definitely will want to become a research partner, and that's called APOP, right? The university program have broader reach and branding with the event sponsorship. And then the AP is called academic partnership. That's much selected with professors, and these are research-oriented activities with grants and gift and the normal or apply DoD's project together. And these are all research partnership. So we cover both sides, research. APOP. The third area I haven't mentioned too much about APOPs. We also cover some of the startup company that may be a spin-off out of the professor's research. And these are in the early stage, they may not have a lot of funding to go buy tools and set up the commercial things. And Synopsys can help you in the early stage be able to get the whole process in place for the startup and future even partnership together with some of the Synopsys tool ecosystem that including some sort of API access to Synopsys tools.
That's very helpful. So I guess we are running out of time. Iran and Zhongyi, do you have anything to add before we conclude the panel?
No, thanks, Ian, for moderating the event, and also thanks for all the prominent speakers. I feel all the talks are very informative and very impressive. I think this event will share the light for all the scholars in our community. Actually, when I saw the attendees, I saw many familiar names like professors and also people from industry. I really enjoy. So yeah, I actually have no, as I mentioned earlier, we will read after confirm with all speakers, and then we will release the video on the YouTube channel. Then I think everyone can watch the video for all the talks and the questions. Yeah, again, and of course everyone can send emails to the speakers accordingly. Okay. Thank you.
So one last thing, we just got quite a few questions coming in. Let me just quickly answer them to kind of conclude the panel. The question is actually in one area is about the scaling of the technology regarding the ACE and the hardware security. I think scaling is an interesting point. For the ACE, the goal is to scale. I think the ultimate goal is to fabricate not for the ACE program and not to fabricate a chip, but for the technology is to be prepared for, I think around like a 20 nanometers style or even more advanced technology. Okay, so, okay, thanks. So one last question for Ahmad. I think it's very dedicated. Side channel are most common review that reject many papers. Can you comment on this?
What again? Side channel what?
Repeat the whole question. I see a growing prejudice towards enclave-enabled application research.
That's not
right?
fair
So
to Ahmed to answer that question.
And the side channel are the most common review that reject many papers, which they claim that the moment you have a paper, they would say that you cannot prevent side channel, so they reject that paper. So you are one of the review. Yeah. Comment on that.
I agree. I agree. Because side channels like blockchains are getting too many. And, and as I said, many of these side channels have the same principle. And it is a matter of engineering to go this way or that way. And this is the reason why people are, to make it in a very blunt way, or bold ways, yeah, people are sick of seeing too many side channel attacks. But I think if you have interesting attack, let's say some architecture that is open, like RISC-V architecture, claims to have side channel protection, and you break into it, like for example, let's say one of these, let's say I take RR design, Cure. You take Cure when it is published, and you ask us to give you code. We don't give you the code. You will make the code yourself, and then you break into it, and then you see, hey, I have a paper. Because if you attack SGX for the the end time, that is not going to be very exciting. That's the reason. So I do not really condemn what PC members do. I know that the security community is very harsh with reviews. I understand it happens to my group as well. But indeed, people think that there are enough sites.
Okay, okay, thanks. So we are really like run out of time. So thanks for attending the panel. Feel free to ask the panelists questions, and feel free to contact Iran or Zhongyi for any organizing or the release of the videos. So
yeah, thank you very much for the invitation. I just want to thank you for the moderation, and it's also good to see friends again
during this time. Thank you.
Okay.